A key fact of life for sections 6.1 through 6.3 is this theorem, the central limit theorem. And it says that if a population has proportion p, then the collection of all possible sample proportions for a fixed sample size n is centered at the actual population proportion p. So if you look at all the possible p hats and were to do a histogram of them, it would be centered. They would have mean p, the actual population proportion. The standard error, which remember is the standard deviation of the sample proportions, would be given by this lovely formula. Standard error equals square root of p1 minus p over n, and would be approximately normal. And you want to have maybe n at least 30 or more. A normal distribution is good approximation as long as n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So if n is very close to 0, and if it's very close to 1, you're going to need a large sample size for this to work. But in practice, that's not an issue. So let's see how this is useful in action. Suppose we're given that 43% of US phones are iPhones. So that's the P. P is known to be 0.43. Then you could ask this question. What is the probability that in a sample of 600 randomly chosen people, less than 40% of them have iPhones? So this is the kind of question that that central limit theorem will let us answer, and let's see how. So if you look at all the possible sample proportions, the average is going to be 0.43. Some of the times with a sample you'll get more than 43%, sometimes you'll get less than 43%. And the standard error, well, you plug these numbers into the formula, you get 0.02. So the sample proportions are normal, centered at 0.43 with standard deviation 0.02. So we're asking what's the probability that we get less than 0.4 when we have this situation. Mean 0.43, standard deviation 0.02. So we know how to do questions like that. This is just our normal distribution problems, except instead of talking about the average amount of sales at a store or something, we're talking about these sample proportions. So the average of all the sample proportions is 0.43. We're interested in 0.40, and it would have a z-score of negative 1.5. And so then with the help of stat key, you get our answer, 0.067. If the population proportion is 0.43, then the probability of finding a sample proportion below 0.40 in a sample of size 600 is about 0.067. Questions like this can be reduced to questions about the normal distribution. The central limit theorem tells us that the sample proportions follow normal distribution, and then we can use all of our z-score and normal distribution tools and stat key, etc., etc. So now let's talk about confidence intervals. Suppose we sample 800 voters, randomly chosen voters, and find that 52% of them are planning to vote for our candidate. How can we create a confidence interval for the proportion of all voters planning to vote for our candidate? Well, whatever the population proportion actually is, it's probably pretty close to 0.52. So the standard error of the sample proportions is very close to square root of 0.52, 1 minus 0.52 over 800, that yucky formula, which is 0.0177. So the possible sample proportions for size n equal 800 is centered at the true population proportion, whatever it is, the thing we'd like to know, and have standard error 0.0177. I suppose we want a 90% confidence interval. Well, we use stat key two-tail, and we see that the z, which corresponds to the middle 90% in here, the standard normal distribution is 1.645. So in our book's language, z star equals 1.645. It's the z that goes with the middle 90%. Whatever the actual proportion is, 90% of the sample proportions are within 1.645 standard errors of it. This tells us that we can be 90% confident that 0.52 we found in our sample is within 0.03 of the true population proportion. Why 0.03? Well, that's our 1.645 times our standard error, rounded to 2 decimal places. This tells us that we can be 90% confident that the 0.52 we found in our sample is within 0.03 of the true population proportion, or that the true population proportion is between 0.49 and 0.55. And that 0.03 is called the margin of error. In general, the formula for confidence interval is p hat plus or minus z star square root of p hat 1 minus p hat over n. And here z star is the z-score from the standard normal corresponding to the level of confidence we want. So remember how I got that for 90%? I used my standard normal distribution and did two-tail and found the z that went with the middle 90%. And in practice, we won't really be using this formula, but it's good to see that where it comes from and it's not magic. How about hypothesis testing? Suppose we sample 800 voters and find that 52% are planning to vote for our candidate. Can we conclude that we're winning the race? So what we're really asking is, if the race is tied, would it be surprising to find 52% out of a sample size of 800 who are supporting our candidate? 50% seem high if the race was tied, if it was actually 0.50. So we're looking for the p-value of a hypothesis test. If the actual proportion is 50%, 0.5, then how likely would it be of getting 52% or more in a random sample of 800 voters? That's what hypothesis test tells us. That's the p-value. It tells us how surprising the data we observed would be if the null hypothesis is correct. And in this case, the null is that the proportion is 0.5. Well, if the p does equal 0.5, then the standard error would be 0.5, square root of 0.5, 1 minus 0.5 over 800, which is 0.0177. So now we find the z-score corresponding to 0.52. Well, 0.52 minus 0.50 over 0.0177 is about 1.13. So using stat key, we put in 1.13 for a z and right tail, because we would know how surprising it would be that we'd get a number at least that big, and it's 0.129. So if the true population proportion was 0.50, there'd be about a 13% chance of finding 52% more support in a sample of size 800. In other words, what we found, the 52% we found, is just not statistically significant. It doesn't really statistically look different from 50%. We cannot be confident that we're winning. And that's something we should have suspected because our confidence interval with the same data contained 0.49, so we might have been losing by 1 percentage point. So that's a very brief overview or introduction to how to use the central limit theorem to answer basic probability questions, but then to do confidence intervals and hypothesis testing.